So in this video, we're talking about the imperial formula detection and how this works. So we start off by looking through our items that we're going to use in this lab. So you've got tongs, basically, a crucible, a lid, a strip of 25cm magnesium, a Bunsen burner, as well as a stand and a triangle to hold on. We've also got safety goggles for eye protection and gloves for our fingers. So the first step is we roll our magnesium into a tight strip, placed in our crucible, and then we weigh first our empty crucible and then secondly our crucible with the magnesium strip in it. Now we are lighting our Bunsen burner to heat. First step is you heat the magnesium strip on with an open lid of the crucible till the magnesium strip starts to burn. Now we'll see this in a second. So as you can see, there is the Bunsen burner burning with the open magnesium strip in it on the crucible, and we're waiting till it starts to ignite. And then once this happens, so you got to make sure your Bunsen burner is in place, and then once this happens, which will just be in a few seconds. So once this is happening, as you can see there, just briefly, the magnesium has started to oxygenate, and from there we are placing the lid on the crucible, so no more oxygen is allowed in, and then you take off the Bunsen burner to stop it from burning, to wait for it to cool down and stop that oxidizing process. And then once this is stopped, we place the Bunsen burner back on, and we then ignite. We then slowly let our magnesium strip burn for roughly about 10 minutes, and then every 2 minutes we were checking it to see how far along the process it is. And then ideally, in the end, so this is a bit of a time lapse here of it happening. Ideally, in the end, what you're looking for is almost a white powder of the magnesium being oxidized, and from then there's no more reaction occurring. That'll happen in a second. So that's, again, once I said, you're checking this every 2 minutes for roughly a 10-minute process. We went a little bit longer due to altitude. So there's the finished product, which is a fully burnt out 25cm strip of magnesium. And then once this has happened, we take our Bunsen burner off and wait for the magnesium and the crucible to cool down. Once it is cooled, we then place it on the bottom of our stand to rest and cool down, as I said. So once this is cool enough, due to time limits, ideally you want to let it cool completely. We put it along with the crucible back onto the scales and weigh how much we have left. And then once that has happened, we record that data. So this is just going through my data. So up the top there you can see is my table. The first one is obviously the empty crucible and lid, the crucible with the unburnt magnesium and the crucible with the burnt magnesium. So the first equation there is just determining the mass of the magnesium used. So you're just obviously doing the mass of the crucible with the magnesium minus the crucible by itself, which gives you 0.32 grams of magnesium. Then we're finding the molar mass out of the magnesium, which is a simple equation again. So it's just 1 mole of magnesium would equal 0.32 grams of magnesium over the molar mass of magnesium, which is 24.3, which gives you 0.13 moles. And then our next equation, you're determining the mass of the oxidized magnesium. So we are just simply taking the empty weight of the crucible plus the crucible with the oxidized magnesium, so which gives you an answer of 0.47. So as we can see for the next equation, which is determining the increase of wet mass, is 0.15 grams due to the oxidization. And then so for the fifth one, it's basically the same as the first. We're trying to find the molar mass of the oxygen atoms, so we put the mass of oxygen used, so 0.15 over the molar mass of oxygen, which is 16, which would give us an answer of 0.010 moles. And then this leads into our question 6, which is where we're trying to calculate the ratio of magnesium used, moles of magnesium used and the moles of oxygen used in a ratio. So we're doing the smallest, which is moles of oxygen over itself to get 1 mole, so it's 0.10 over 0.010 over 0.010, which would give us 1 mole. And we're doing the bigger over the small, so 0.013 mole of magnesium over 0.010 mole of oxygen, which would give us a ratio of 1.3 to 1. So this leads on to our next page. So question 7, it asks us what the imperial formula for this would be, and basically because it's almost a 1-to-1 ratio, it would just be MgO because it's 1-to-1. And then going on to question 8, we're trying to find the percent error, so it would be 1 minus, which is the accepted value, minus 1.3 over 1 times 100, which would give us 30%, which is our percent error. So this leads on to our next question, which asks us to identify the major errors in the experiment which caused the ratio to be affected. So a few of the main ones were definitely, or all of the main ones were definitely human error. So whether it was inaccurate measurement of burning, or how hot we were burning it at, or how long it was exposed to oxygen, or basically anything like that. So all the major causes were human error. So in this last page, on question 11, we are talking about interpreting the subscripts of ethane, which is C2H6. So obviously, and in terms of what atoms are in it and what moles. So obviously we have 2 carbon atoms and 6 hydrogen atoms, which is obviously. But then we also could have 1 mole of ethane, which is C2H6, but we could also have 2 moles of carbon and 6 moles of hydrogen. This lastly ties into our last question, which is develop a hypothesis. At a high temperature at which the reaction takes place, a green-yellow solid may also be formed. Propose a hypothesis about the chemical nature of this product. So my hypothesis about this is basically, I think what is happening here is the magnesium has been burning with another chemical in the air, because we're not in a stable lab. For example, the chemical, like, there might not be a perfect reaction with the oxygen in the air. There could be some other unstable gases or some other gases in the air, which is my main hypothesis of why this might have happened. As a bit of a concluding statement, just over a couple bloopers here. So this ties in with what we've been learning a lot about in class recently, because it involves not only naming of chemicals, but like figuring out what is happening in a chemical reaction. For this one, it was obviously magnesium being oxidized, and like what I found, like, as well as not only that we were learning from class, we were also doing things like using the equations we've been using to find out the molar mass of things and stuff like that. What I found really interesting about this prac was, although my partner and I thought we did this extremely well, it turned out that even with how well we did it, we still had quite a high inaccuracy rate, which ended up about a 30% inaccuracy rate, which kind of surprised me, considering like how perfect you can do it, but it's still not like exactly to the point. I didn't really have any other questions about this. I talked to my teacher and my classmates a lot about the extra questions, but going through that all, it made a lot of sense, and I found this prac quite enjoyable. Once again, thanks for watching.